To better understand how to design finite state machines, we're going to walk through a finite state machine design problem. Okay, so here's a problem. It says for the following circuit, provide a PSNS, which stands for present state next state table, and a state diagram that describes the circuit. Include the output variable Z in both the PSNS table and the state diagram. Be sure to provide a legend for your FSM. Alright, so we're going to walk through this problem. The first thing that you want to do when you look at finite state machine problems is to just sort of look at the circuit and observe what you have. You can see here I have two state registers, or rather two state flip-flops. Both of them are JK flip-flops. And here we have the, I'll go ahead and draw, this is our excitation or next state decoder logic, and this here is our output decoder logic. So these variables y2 naught and y1 and y2, etc., these are all here. So it was just drawn like this so wires wouldn't be all over the place. But basically you can consider these as connected to these other outputs here. Okay, so as I mentioned, this that I circled over here is the next state decoder. And this is the output decoder. And the flip-flops in the middle are our state registers. Okay, so some things to note is that we have two state registers. So the number of states we could have, number of possible states that we can get with state registers is 2 to the number of registers, or flip-flops. So in our case, because we have two state registers, we can have a total of 2 to the 2, or 4 possible states. Now we also want to note that our output is a function of the state variables y and y1 and y2, and also the function of the input. So this is going to be a Mealy output because the output is a function of both the external inputs and the state variables. Okay, so the first step we already took care of. We noted some pertinent information. We know it's going to have a Mealy output, and we know we're going to have a total possible number of states of 4. So the next step is we can go ahead and write down the equations, excitation equations. And we can just look at this. We've got our, I'm going to call this J1 and K1 and J2 and K2. So we have J1 is going to equal Y2. We have K1 is going to equal Y2 and X. Then we're going to have J2 is going to equal X. And K2 is equal to Y1 exclusive NOR X. Alright, so we wrote down our excitation equations. We can also now write down our output equations. And we only have one output, Z, which is a Mealy output. Z is equal to Y2 naught X naught, or Y1 Y2 X naught. So we just looked at what the circuit logic was to write down our equations. Alright, the next step is to go ahead and create our present state next state table. So in the present state next state table, you first write down your present state variables. So our present state variables are going to be y1 and y2. So I'm going to call this present state. We're going to have y1 and y2. And then we also want to write down our inputs. And in our case, we only have one input, so we're going to put X. Okay, so we have those 3 columns. Then we also want to add in the excitation variables. And here we're going to have 4 of them. We have J1K1 and J2K2. Alright, then we need our next state variables. Next state, we're going to call them y1 plus to represent the next state of y1, and y2 plus to represent the next state of y2. And then we're going to have our outputs. So every PSNS table is going to have these following columns: the present state, the inputs, the excitation variables, the next state, and the outputs. Okay, so we're going to treat the present state and the input as all possible inputs to this circuit. So because we have three variables here, y1, y2, and x, we're going to have 8 possible input combinations. So I'm going to go ahead and write that in. We're going to have all zeros. 1, 2, 3, 4, 5, 6, and 7. Alright, so we listed all 8 possible combinations of our inputs. And now we have to go ahead and figure out what our excitation variables are with these given inputs. So that's where the equations come in handy. So J1 is equal to Y2. So here's Y2. So J1 is going to be the same exact thing as Y2. So we're going to have 0, 0, 1, 1, 0, 0, 1, 1. Okay, what's K1? K1 is Y2 and X. So here we have Y2 and X for the first row is 0 and 0, which is a 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is a 1. 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. And 1 and 1 is 1. Alright, J2. J2 is equal to X. So now we list J2 as whatever it is. Whatever X is. So it's 0, 1, 0, 1. 0, 1, 0, 1. And K2 is going to be Y1 exclusive NOR X. So remember, the exclusive NOR is checking to see whether the inputs to the exclusive NOR are the same or not. Okay, so Y1 and X are both 0, so our output K2 is a 1 because they are the same. Again, here we have Y1 and X are different, so the exclusive OR NOR will output a 0. Y1 and X are the same, Y1 and X are different, Y1 and X are different, Y1 and X are both 1, so they're the same. Now they're different, 1 and 0, they're different, 1 and 1, they're the same. So I would end up with this column as my K2. Now to determine the next state, we need to look at the excitation variables and the present state. Okay, so remember in a JK flip-flop, if both J and K are 0, that means we hold. I put up the characteristic table of a JK flip-flop right here to remind you that when J and K are both 0, you can see Q next state gets whatever Q is. Alright, so for Y1, we're depending on J1 and K1. As you can see, this is our JK flip-flop, which is our Y1 state variable. So our next state Y is going to be holding whatever Y1 was, and it was a 0. So my next state for this first row is going to be a 0. Now J and K are both 0 again, and my Y1 was 0, so it's a 0. J is 1 and K is 1, that's a set condition, so I'm going to get an output of a 1. J and K are both 1, which means toggle. So I had a 0, I'm going to get a 1. J and K are both 0, that means hold. I have a 1, so I keep a 1. J and K are 0, that's a hold, so I keep a 1. J is 1, which is a set, I get a 1. J and K are 1, which means toggle. I had a 1, so I get a 0. So that's how I determine that column. Now Y2 is going to be dependent on the J2, K2 variables and the present state Y2. So now J2 is 0, K2 is 1, which is a clear, so Y2 next state is going to be 0. J2 is a 1, which is a set. K2 is a 1, which is a clear. J2 is a 1, which is a set. They're both 0, which is a hold, so what is Y2? Y2 is a 0. They're both 1, which is a toggle. Y2 is 0, so Y2 next state is 1. Both a 0 is a hold. We hold on to the 1. And then 1 and 1 is toggle. Y2 is 1, so we get a 0. Alright, and last but not least, we have the output. And the output equation we have already written here. It's y2 naught and x naught, or y1, y2, x naught. Now remember, the key thing is that output depends on present state. Big underline here. A lot of people mess up and use the next state for their outputs, but no, it depends on the present state. So you got to look all the way back on the left side of your table. So our output Z is depending on these three columns, the present state of our state variables y1 and y2, and the input x, and we have this equation. So for the first row, x is a 0, so x naught is a 1. Y2 is a 0, so y2 naught is a 1. So we have 1 and a 1 will give us a 1, and anything ORed with a 1 is a 1, so the output is 1. And you just have to go through this table one row at a time. So now we have x is a 1, which means x naught is a 0. We already know this term is going to be 0. And again, x is a 1, so x naught is a 0. We know this term is going to be 0, 0, or 0 is 0. And I'm not going to go through every single row in this case. I'm just going to go ahead and fill out the rest of what it should be. You can practice it on your own to see if you get the same thing. Just going row by row. Alright, so we have now completed the PSNS table that was asked for in the problem. That included our outputs and our next state variables. Now we can use this table to draw our state diagram, and that's what I will be doing in the next lecture.